All right, perfect. One was there as well. All right, wonderful. Thank you very much for this wonderful introduction, and congratulations to you, Professor Reddy, for an incredibly popular webinar series. That's amazing. I'm humbled to be here, so thank you very much. I'll try to entertain you for the next 55 minutes, roughly, and hopefully give you some ideas. Um, and I want to start with what really motivates me to do the work that I do. And it all starts with the concept and something that I read in, I think it was around 2008. And it's from a book that came out in the 1980s called The Collapse of Complex Societies. And it's this graph here that I really liked. So the book is all about governance and government institutions and how when a society becomes more complex, so you basically have to build things, have more so infrastructure and more government departments, and so um, there's that axis here, which is complexity. So just think of a civilization starting, just think of a city starting, and you're going to have to build stuff, put stuff, so it's becoming more complex. And here on that axis, we have the returns. So these are the benefits. So we're investing in building something, and what are the benefits that we're getting? The example that I like to use for me is I settle down somewhere new, for example, in Chicago, and I know I'm going to need some water for all my residents. So what I'll do is I'll build a big system and I'll really put a lot of pipes and maybe water treatment plant and really add a lot of complexity. I'm going to get a lot of benefits from it. And then the city grows and grows and grows. And at some point, we're so far away from the lake that we can't pump water from the lake anymore. We might have to go to the ground. So again, we'll have to put a lot more complexity, probably as much as we had at the beginning. But now we don't tap the first best option, it's the second best option. So the benefits that we get are lower. And then we grow and we grow again and we put more. And again, the benefits are lower. And then again, the benefits are lower. And this is called diminishing marginal returns. So the marginal returns, the benefits from that added complexity, they're getting smaller and smaller and smaller and smaller. And at some point, you have to change, you have to adapt, you have to evolve, or otherwise you're going to collapse. And we've had many examples in the history of mankind. Collapse, we have the Roman Empire, we have the Maya civilizations, tons and tons of examples. Usually you lose a lot of complexity, you lose a lot of infrastructure. And so, yeah, so you lose a lot of benefits, or you have to adapt and evolve. And we've had many examples of that as well. In the Roman Empire at the beginning, with all the waterworks that they did. And the one that I like in particular is the Industrial Revolution. So we use coal, we use fossil fuels. This is amazing energy packed in a very small volume that we've been burning, and it's really enabled us to progress and to grow, and it's been absolutely amazing. And of course, it's brought its own problems. And so we were there maybe in the 1800s, but now we're pretty much here. And so we have to do something about it. And that brings me to my first favorite quote, which is from Einstein, and it's we can't solve our problems with the same thinking we used when we created them. So I like to say that my work is all about infrastructure, and we'll talk all about it. In particular, what I'll do in half of this talk is really explain how infrastructure works. And then the second half, we'll talk a bit more about the future and sustainability and some of the major problems or major trends that we're facing now. But I like to say that I'm looking at those old systems in a new way. I'm really trying to be creative. Give me 1 second here. Perfect. And so when I look at this here, this is a picture of Chicago. What do you see? A transport person might see the roads here. An environmental person might see the water or some of the green things. A solid waste person may think of all the waste. A building person is going to think of all the structural here, all the building, the energy that's being used in those buildings. And the reality is that cities are all of those things. So what I try to do is to really try to look at them entirely holistically, looking at all those infrastructure systems. And more particularly, I focus particularly on seven. So by training, I'm more of a transport person, but I've been doing a lot of work with water and wastewater. But then I also look at electricity consumption, gas consumption, a lot of waste, and telecommunication. I'm convinced that telecom right now is part of computer engineering or electrical engineering, but it is a civil infrastructure system. So for those of you in civil engineering, I really think we should embrace telecommunication infrastructure as our infrastructure. We should learn how it works and think about it for the future. And that's going to be the last one. So toward the end, we'll talk a little bit about the future of all these infrastructure systems. But again, my goal right now is to go through a whirlwind of how these things work. Right, that's what we're going to do right now. So if this is undergraduate level stuff, even maybe high school for some of you, But I promise you've forgot a lot of it. So if you're a water engineer, you learn something with electricity or solid waste. So very quickly, we'll start with water. With water, there's three big elements. One is water collection. We've got to get the water from somewhere, whether it's from the ground, whether it's from surface. Then we have to treat the water to make sure that it's potable, and then we have to distribute the water. So water collection, there's a few sources. A big one is surface water. So this is Lake Michigan, huge Lake Michigan, one of the Great Lakes. There's also rivers. This is, where we can get fresh water. We can directly tap into it. Another option is the ground. Groundwater, 30% of all the fresh water on Earth is actually in the ground. So we'll tap into it either to an unconfined aquifer or to a confined aquifer. And then in the last, I don't know, maybe 10, 15, 20 years, 15 years now, we've also become much better at desalinating seawater. So we can take seawater, we can treat it, and then we can remove the salt from it. So we're getting better at it. This is a picture of Singapore, if you've been there. All of this here, all the land that you see there, did not exist 40 years ago. This is all reclaimed land. This is all rocks imported from Indonesia, put into the ocean to form this new land of Singapore. Then what they did is I'm lying a little bit here because this here, they actually have a dam, and this is all fresh water. So they built a massive freshwater reservoir out into the sea because Singapore is so small, they don't have any big lakes or reservoirs. So they had to, build this. Yet Singapore still desalinates a lot of water. And that's a big source, again, of water now for some countries, especially those that don't have access to fresh water, like Singapore and like Israel. Water treatment. How do we treat water? Well, there's a pretty consistent way of doing it everywhere, which is basically we remove the large stuff first. So we're going to get water wherever we can get water, whether it's surface water, groundwater, or if we don't have access to fresh water, it's going to be seawater. Then we're going to use physical means to, like screens, just to get rid of some debris. Then we'll have the coagulation, flocculation process. So this is here in your raw water, you always have little particles. They're negatively charged, so they're like magnets that just repel one another. So first we're going to neutralize them. And then once they're neutralized, they can form flocks, and they're going to be heavy, and they're going to fall to the bottom of the basin. So that's the sedimentation. So we've removed almost everything. We'll have one more filtration process, and then in final disinfection. Now, wherever you go to a water treatment plant, it's not going to be like this. It's always, every treatment plant is different because it's tailored often based on the raw water that they get. That's one. And also based on when it was built, based on the technology available when it was built. I remember at some point visiting a water treatment plant in Omaha, and there they have 3 water treatment plants, and we visited one, and I asked the people there who knew everything, it's like, how is it different from the 2 others? And they didn't know. They didn't know. You tend to be really tailored to your own way, to your own techniques, to your own process. But this is, what I'm showing here is the general process. With reverse osmosis, so that's to desalinate fresh water, we do the same thing until the filtration, and then we have another process. We have a membrane, and we push water, the seawater, what's left with the diluted salt into the membranes, so that the only thing that comes through is the pure water. And then we collect that pure water, and pure water is actually not good for you because you need mineral. So then we have to remineralize it by putting a lot of limestone into it, and then we can distribute it. Distribution is the next step for water. And the way that we've been doing it for a long time is we get the water from somewhere, for example, lake. We do purify it, make it potable in a purification plant, in a water treatment plant. And then when it's perfect, then we'll distribute it in a network of pipes. And there we have to be very careful because the pressure here has to be very high to make sure that no water leaks into. So from the ground, there's going to be water in the ground. We don't want any water in the ground to leak into our system because that water could be contaminated. So those systems here, they're always under enormous pressure to make sure that water that's pristine when it comes out of the plant here arrives in an almost pristine way at your house. This is the way we've been doing things for about 100 years, over 100 years, and I think it doesn't make sense. I think it's a ticking time bomb, all those always under pressure pipes, and then we have a water main break, and we have to dispatch an emergency crew, we have to change the pipe to put another one. So this is really, for me, a problem, and we really should rethink distribution. And I had an epiphany, not an epiphany. I was stunned in 2019. I spent some time in Vietnam, and I thought that the system that they had in Vietnam was vastly superior to what we had in the US. And I'm glad that here I have a lot of people who are in India. I know it's very similar in India. So here's an example. The way we do it here is we get water wherever it is. We treat it. And then we have this system of pipes, of high pressure pipes, always high pressure, to make sure when it gets to the house, it can go to the upper floors. You don't need a pump or anything. In Hanoi, the way they do it is basically they had different neighborhoods and they would shut off access to water because they didn't have enough water for everyone. So what they did is the first part here is the same, but every single house, they built they have a tank, a fairly big tank actually in the basement. And it's in the basement. This way, even if there's not much pressure from the water treatment plant, it just by gravity goes into the basement tank. And when it's there, then they pump it up to the rooftop tank. And then they always have water that's there. So even if there's no power, they don't need a pump to be operational here. So it's a rooftop there forever. And then with gravity, it just goes to all the faucets in the house. And there, because when it comes out of here, we know it's good to drink. When it's here, we don't really know. So then they have another filtration process, which works really, really well. So there's, of course, problems in everything, but I thought this was way more resilient because when I was there, actually, they had a problem with contamination. Houses just stopped their access to the water from the pipes, and they were still for 3, 4 days. They had as much water as they wanted, thanks to their basement tank and rooftop tank. And then we do have a lower pressure system here, which means also that we're consuming a lot less energy for distributing water. So this is all about water that I want to talk about. If you don't know about water, learn more about it. It's absolutely fantastic. Now we'll go to my favorite one, which is wastewater. That's my favorite of all time. You should know that there's two types of wastewaters. There's sanitary wastewater and stormwater wastewater. So stormwater is whenever it rains, water has to go somewhere. We don't want to use it. We got to get rid of it. So that's one form of wastewater. The other one is when you take a shower, when you cook, when you go to the toilet. That's the sanitary wastewater. And that's one we want to be very careful about because it's full of contaminants and it's heavily polluted. So how do we deal with them? Well, there's again two ways. One is to have a combined system for the two. So see here we have the house. By gravity, all the wastewater is just going to go to the bottom of the house, and then we're going to link it to that drain here in the middle of the road, always at the lowest level to make sure that gravity does all the work. And then whenever it rains, water goes to the gutters, the catch basins, and then it enters into the sink. So this is how most older cities do it. Basically, the drain here for the flooding was there for a very long time. And when we started to distribute water in the late 1800s, we started to have a lot more wastewater. So we had to get rid of it. The cesspools in the basements were not enough anymore. And building a separate system would have been very, very expensive. So we just linked every single house to that common drain here. This is a big decision that cities came to regret because now whenever it rains a lot, this overflows and we get a lot of sewer backups. So what's much better now, at least after roughly World War II, 1960s and 70s, we always separate sewer systems. So here we have the sanitary sewer pipe, and this is fairly predictable flow and it's fine. And this is here the storm drain. And even if this overflows, it's okay. First of all, we don't even treat it. We just dispose of it directly in a natural body of water. And even if it overflows, at least it's not in sewers. It's not in the people's basements. So separate sewer system, much better. Retrofitting older system like this with a separate really would be very costly. And so we have to think of solutions. And the big solutions that came about in the 1960s was to have deep tunnels. So this is how the system is in Chicago. We have the city here. We have the combined sewer system that's here. And then they built, since the 1960s, very deep, huge tunnels, amazing tunnels that cost billions and billions and billions. And all the overflow, instead of going into people's basement, or at least not as much in people's basements, and we try to avoid it to go in the body of water like the river, it goes into those deep tunnels. And then they're led to old quarries because these are giant pits into the ground. And we just dump all the water there whenever it rains. And when it stops raining, we pump it to go to the wastewater treatment plant. This is a typical 1960s, 1970s solution. We think it's more resilient. It's not. The system really can't handle that much rain because since then the city of Chicago has expanded a lot. And so really now we're being more sustainable. We're thinking a bit more, I'm going to say rationally, because why do we do this? We do this because our sewer system overflows. Why does our system, combined sewer system overflows? Well, it's because whenever it rains, the water goes there. Why does the water actually go in the combined sewer overflow? Well, it goes there because all the surfaces, so all the roads and the buildings, they're impermeable. As in water falls, it doesn't have anywhere to go. So just with gravity, it just follows gravity and it goes into the sewers. So now we're really rethinking in the past 15 years, pretty much every city on earth, as far as I know, is really embracing green infrastructure. This is an example in Chicago where we have here, it's permeable pavers. So it's pavers, but they're not stuck. There's a little groove. And when water trickles down, there's actually gravel, but the gravel was selected so that it's fairly coarse and there's a lot of void space, so filled with air. So when it rains, that air is just leaves and it's filled with water. And so whenever that overflows, then it goes into planter. And when that overflows, then it goes into the sewers. And this works really well because when water falls, when it rains, then you just keep the water locally. You don't send it to sewers, you keep it locally. So this is a great example of, again, this is green infrastructure. It's also called low impact development. As far as I know, every city in the entire world faces flooding problems. Even cities without much rain, when it rains, it pours. So they all have flooding problems. And this is really transforming cities everywhere in the world. And I've been to a lot of cities in the world, and everywhere people are embracing that concept of green infrastructure, which I find amazing. And that's why it's really my favorite type of infrastructure, because it's really changing, transforming cities in the entire world. And the funny thing is, it's not even something that we're dealing with directly, right? I mean, it's stormwater. We don't consume it. We consume water, we consume transport, we consume electricity. We don't consume wastewater. And yet that's the wastewater, that's stormwater that's changing cities everywhere in the world. So, all right. So now we did water. Then we did wastewater. Now I want to bring you to transport. And especially I want to talk to you about congestion, because congestion is really the plague that affects cities, that affects people, that annoys people. I know, Professor Reddy, you live, fairly far away from the campus, so you're probably stuck in traffic every day. And my question to you is, how do you ease congestion? And the natural way of thinking, again, the 1960s, the engineer of the 20th century, what you think is, well, clearly there's too many cars, not enough roads, so the answer is to build more roads. But that's not necessarily the good solution, at least in a city where you don't have more people coming in. If you're doubling in population, sure, you need more roads. If not, you should rethink a little bit what your problem is. And you should think there's really two kinds of solution. Sure, one is to increase the supply, to add more roads. That's one, granted. But again, if your population is not increasing, chances are you don't need it. The other one is to reduce the demand. And now you're going to think, what is the demand? So supply and demand for transportation. Supply is the roads. That's amazing. No, that's obvious. What about the demand? What's the demand? What is demanded? And think about it, really, what is demanded? And when you really think about it, what are we asking for? We're not really asking for mobility services. What we're asking for is space. We're asking for physical space over a certain distance. And so basically, if you reduce how much space people take, then with the same supply, you can have more people traveling. So in this photo here, what we have is 60 people. If they're on a bus, that's how much space they take. If they're biking, roughly, that's how much space they take. Or if they're walking, and if they're driving, that's how much space they take. And that's why the car is really not conducive to beating congestion in a dense place, because just it takes too much space. Here, I like this. This is from in Austria. Some politicians really wanted to drive the point across, saying, put more bike lanes, because look, if we're not on our bikes, this is how much space we would take. So, think about us as well. And that's so much true, because again, it's the space. Of course, there's transit, and people take a lot less space if they're on a bus or a tram. And so my answer, always what I tell people, is always say yes to more investment in transit, especially people who hate transit. If you're like, I don't like transit, I don't want to be surrounded by people, it stinks, it's full of germs, I want to stay in my car, then you should be saying yes even more to transit. Because everyone who's not in transit, they're in the car on the road creating congestion. So always say yes more transit. Always, always encourage. Always say, please use my tax dollars to invest in transit, because otherwise you're going to face more congestion. And the other concept, which is not so much the transportation the offers, it's on the other side, is the concept of land use and making destinations closer. So this is here the concept of the 15-minute city. And this is the goal where within a 15-minute walk, you have access to essential amenities like a grocery store, like a healthcare facility, like a school. Doesn't mean that you must go to your neighborhood grocery store, but there's one there. And if people do more things fairly close to where they live, then again, there's going to be fewer people on the roads. And for the people who do drive, it's going to be a lot less congestion. So always think in transportation, what's the solution? Really think, if you're doubling in population, if you're increasing 20% in population, you will need more roads. But if not, you don't need more roads. You should really think about, again, having less space per people. That's why you see carpool lanes, for example. And then it's really making those destinations closer. So if you're driving 10 kilometers, or if you're driving 5 kilometers, the amount of space that you need in 5 kilometers is half what you need for 10 kilometers. So the amount of congestion that you generate is half as much. So really placing grocery stores, placing schools, placing all of those within not too far from where people live has a huge impact on traffic congestion. That's all I'm going to say on transportation. Told you it's a whirlwind. It's 9:26 right now. Really want to go after. So now we'll go to electricity. And in electricity, there's 2 points. First, just generation. And then once you've generated electricity, there's the transmission distribution. With generation, we have to know that in the 1800s, we found that the best way really to generate electricity was through a mechanical movement. So we're turning a rotor around a stator with coils, and then we can generate a current, which means that because we want that rotation, the best source of energy that we can use is mechanical movement. The other thing is that unfortunately, with electricity, we cannot mine electricity. We cannot store electricity very easily. We have lakes of water, not lakes of electricity, or no mines of electricity. So what we'll have is always harvest one source of energy and turn it into electricity. Here I'm showing quite a few. I'm dividing it here into a thermal, kinetic, and other. So thermal and kinetic, all of those here really rely on that movement. And there's different ways to do that. One is to harvest kinetic energy in the first place, hydroelectric power plant. So that's with your dam, tide power, wind with the wind turbines, wave power. This is all kinetic energy that we can turn directly into electricity. Here, these are thermal. So what we'll do here is we'll use chemical energy, usually except for solar, but we will use chemical energy we'll use that chemical energy, burn it to generate heat. And with that heat, we'll be able to generate that movement. So in the case of coal and natural and nuclear, we'll generate steam, and that steam will turn a turbine. In the case of oil, we'll burn it, and it's going to be a piston, and the piston is going to turn a turbine. In the case of natural gas, like a jet engine, we're going to burn it, and that just exhaust is going to turn a turbine that can generate electricity. Geothermal, biomass, same thing with the steam, and solar thermal. That's a really cool one, where what we do is we're using the power of the sun to generate steam, and again, that steam turns a turbine. And that's not the same as solar PV, photovoltaic, which is the only other way that we use to generate electricity that does not involve mechanical movement. And so usually, and then I've come back here, I have non-renewable and I have renewable. And I've got nuclear sort of in the middle. So these, they're not renewable: coal, oil, natural gas. These geothermal, biomass, solar, wind, they're all renewable. Nuclear is in the middle because it's not renewable at all. We are going to mine that nuclear energy, those uranium, plutonium, we're going to harvest it, and then we're going to generate electricity, and then we have toxic waste. The only reason why it's there is because it's not sustainable on one count, versus coal, oil, natural gas, that's not sustainable on 2 counts. Because here, not only once I burn the coal, it's gone. Once I burn the oil, it's gone. Once I burn the natural gas, it's gone. Like nuclear, here the emissions are greenhouse gases. And those greenhouse gases, we've emitted so much of them that it's led to a climate change. So that's why here those are particularly bad, because again, not sustainable on 2 counts versus nuclear that's not sustainable on 1 count. Once we've generated that electricity, what we're going to do is we're going to have to distribute it. So this is a picture of the power grid. Here, usually we have those big power plants. So here we have a nuclear, coal, some industrial power plants. Here, hydro. These are going to be located next to where that energy is. In the case of hydro, in the case of wind that we have here. In the case of coal and nuclear, they're usually going to be located next to rivers, because these require cooling, and so we need access to a lot of fresh water. Once we've generated that electricity, then we're using a transmission system, and we're going to distribute it to, this transmission system to the cities. In the cities, we'll have substations, and then substations to distribution systems, and then those to individual houses. So this is your typical transmission system. Let me ask you, how many power lines do you count here? And you might tell me, well, there's 1, 2, 3, 4, 5. There's 5. No. These 2 here at the very top, this is for lightning protection. It's really 1, 2, 3, because whenever we generate a current, we always generate 3 phases. So wherever you'll go in the world, absolutely everywhere, whenever you look at power lines, you'll always see those 3 here, or sometimes 6 if it's double tree. So we have the transmission to the substation. Here we'll step down the voltage from maybe 200 kilovolts to something like 13 volts. Then that's going to go to the distribution system. Look at that, 1, 2, 3. 3 phases, always. In that case, it's a typical utility pole in the US. So those phases here, 13 kilovolts, we're going to step them down to 240 volts in those transformers here. And then those are going to go to houses. And it's actually 240 volts because what you get at home is you get the 240 volts, you have the neutral at the bottom, and then in the middle, you put another one. And so you have two phases of 120 volts. And so if you open your electrical panel, at least in the US and Canada, I'm not sure how it is in many other places, at least in India. So some people, I think in Europe, there usually it's three because there the voltage is 240 volts. But in the US, you'll always see this. And because you have two phases, one here, and then you might see some appliances with the double breaker. Those are those that will work on, instead of doing 240 to 120, 120 to zero, they do 240 to zero. And so they work on 240 volts. That's what you have for the AC here. So 240 volts, higher voltage, lower current, which means that's lower current in the wire, which means it's a lot less fire hazard. If you don't know, go home after, look at this, learn which appliances run on 240 volts. It's very, very interesting. And about this here, I'll tell you more about that. But if you want to learn all about that, I call it pole reading. If you want to, not palm reading, but pole reading. And if you want to learn about it, you should go to my Substack, and you should, in fact, subscribe to my Substack, and I'll tell you more about that at the end. That's all with electricity. I'll move to gas very, very quickly with gas. We have gas wells. We have to get the gas. It's wet gas. We have to separate a lot of the constituents, the chemicals that are in the gas. We do that in a very well in a fairly regular way. The only thing is that we consume a lot more gas in the winter. So then we're going to use gas lines to bring gas close to cities. And then we'll use old gas fields or salt formations or depleted aquifers or other salt caverns. And we'll store a lot of the gas there in the summer and then get it back in the winter so people can use it at home. I won't say too much. If you want to know more, I'll tell you more about that after. The only thing I'll say is that a lot of people ask me, should I have gas heating at home or electric heating at home? And I always say, well, look at your, you should really look at your power grid. How dirty or how clean is your power grid? I use an app. It's called Electricity Maps. You can just all download it. It's this one here. If you can see it, Electricity Maps. And it's got maps of the entire world. And you just click on where you live and you'll see the power grid mix. This is one I got yesterday for Chicago. And I'm always told, oh, Chicago, we're good. We have a lot of nuclear. And I see here, yeah, sure, we have a lot of nuclear, but look at that. Tons of gas and quite a bit of coal, which means that our electricity mix, and that's the average for the last 90 days, is 430 grams of CO2. So it's not great. Illinois is doing okay because Southern Illinois has a much cleaner grid, but Northern Illinois, where we are here, it's not doing too well. And usually, if you're above 180 CO2 grams of CO2 equivalent per kilowatt hours, you should really stick to heating your house with gas, not electricity. But there's a caveat now because we have heat pumps, and heat pumps change a lot of things, so we can talk more about that after if you want. But know your power grid, know how your energy is being, how your electricity is being provided, and based on that, make the right decisions at home if you want maybe to reduce your greenhouse gas consumption or emission footprint. That's all I'm going to say about gas. Now, solid waste, very quickly. I don't know if you know a lot about solid waste. I feel bad saying anything about solid waste because Professor Reddy is a world expert on it. But it seems simple. Pick up the trash, recycle if you can, and discard it. But it's really not that simple. When you look at the functional elements, there's waste generation, waste handling, and the source. So this here, both here, this happens at home. So at some point, you take a product, you say, you know what, this, I don't like this anymore. I want to throw it away. So in 1 minute it has value, the other minute it doesn't have any value. So that's a big gesture. And then where do you put it? Waste handling at the source. Do you recycle it? Do you not recycle it? So this is a big decision. So when you think about solid waste, these are very big things you consider. Then you have the collection, the transfer, transport, separation, processing, disposal. You really have to think about all that. This is the typical inverted pyramid of the solutions for solid waste. The first thing is reduction and reuse, then recycling, composting, energy recovery, treatment, and disposal. Reduction and reuse, we talked about that. So we'll always try to reuse, always try to reduce how much waste you even generate. Once it's there, try to recycle. Recycling is all about taking one waste and changing it, repurposing, transforming it to make it useful. You've seen a lot of those posters everywhere. Composting is a form of recycling where you get that organic waste. With that organic waste, you mix it with air. You let the microbes do the germs, the microbes do their thing, and they eat all the nutrients, and then they leave you with here the humus, and then you can use that for as fertilizer. That's in the presence of air. If you do the same thing, but you do that in the tank with no air, then you have anaerobic digestion. This is an example here. This is a wastewater treatment plant in New York. I gave a talk there last year, and on my way from the airport to the school, I saw this. I'm like, those big X-shaped containers. And I'm like, this is a wastewater treatment plant. I know that. I took a picture. The other thing you can do is to burn the waste. We don't really do that in the US, but many other countries do that. The champions are in Japan. And then you landfill. In the US, what we do is we dig a hole, put a big tarp, put a lot of the waste. At the end, we put a tarp on top of it. And really what's happening is an anaerobic digestion because a lot of food waste there, a lot of microbes naturally are going to eat all that food. Because there's no air, they're going to produce methane. So we're going to use that methane and we can burn it to heat places or to generate electricity. And then we have telecommunication. I'll go very quickly. All I say is it's all about protocols. It's amazing. You should really learn about telecommunication. It's wonderful. Everything that we're doing here today is thanks to telecommunication. That's why I can give that presentation. Whenever you see an antenna that's telecommunication, see these ones. This is what makes your cell phone work. It's incredible, always those white rectangular boxes. So this is my whirlwind of how infrastructure works. If you want to learn more, you can always get my book. This one is with equations. It's a textbook, doesn't talk about gas or telecommunication, but it's very informative. I know quite a few of my students are attending now the class, and I know they're using it, and I think they're liking it a lot. But do yourself a favor. This one is very, very easy to read. It's called the Infrastructure Book. How cities work and power lives. There's no equations, only in the footnotes if you want. There's one chapter per infrastructure system. We travel all around the world. Water collection in Rome, water treatment in Tel Aviv, water distribution in Hong Kong. We go to New York, to Tokyo, to Buenos Aires. We go to Shanghai. It's really, really a lot of fun. If you're at UIC, you don't have to buy it. You can download a PDF for free from the UIC library. If you're not at UIC, buy it if you want, sure, but otherwise get your public university to buy a public library to buy a copy, or your university to buy a copy and read it. And honestly, even if you find a digital copy online for free, get it, read it. I don't care. Making money, I'm not trying to make any money. Making money by writing books is almost impossible unless you're really, really good. The only thing I'll ask you, please, if you read it, that's tiny little ask for you is please give it 5 stars on Goodreads and Amazon. And the reason why I say that is that people are always looking for books to read. And I would much rather people to read a book on infrastructure and to learn how the world around them works than to read a book about, I don't know, social media or something else. So it's really not about my book on infrastructure versus another book on infrastructure. It's really about just reading a book on infrastructure in general. By knowing about infrastructure, you're more educated on how the world around you works. You can also make then a better and more positive change. So please think about it. Give it 5 stars on Goodreads and Amazon, or at least Goodreads. It matters a lot, and it's really one of my big mission right now is to really talk about infrastructure and communicate science. All right, I really want to go. I've taken a lot of time now, but I really want to go more fairly rapidly to the rest. So I already told you my favorite quote in the whole world. I'll tell you my second favorite quote in the whole world. It's from an artist, and it's by Frank Stella, and his boundaries are defining but not limiting. So he has canvases, and what he did over time was to emerge. And his canvas, so the painting, emerged almost like a sculpture. And I like that. Boundaries, so the boundaries of the canvas, he says, they're defining, but they're not limiting. And I say for me, it's the same thing with infrastructure. Usually we limit ourselves to our role. So it's like, I'm a transport engineer. I only look at transportation. I don't care about water. I'm a water engineer. I don't care about transportation. I only do water. And I tell them, yes, the boundaries are there and they're defining. Transportation is transportation. It's not water. Water is water. It's not transportation. But those boundaries are defining. They're not limiting. Talk to one another. Work with one another. And especially because all those infrastructure systems, they're all interdependent. This is here just a map of UIC, and we see there's a distribution line, electrical, sewers, water, buildings, transportation, natural gas. They all live in the same space. They all depend on one another. I'm not going to go over this table, but this is all the interdependencies or some of the interdependencies between infrastructure systems. So we really ought to learn more about them and to maybe better integrate them. So a few years ago, I came up with that matrix of integration decentralization matrix. So what we have here is infrastructure that's more centralized, and here it's more decentralized. Here it's integrated, and here it's more separate. It's separated. And really, where we are here, the 20th century brought us here. We heavily centralized and heavily separated. I don't want to rely on any other infrastructure systems. That's what led us to having those big power plants in that case, or those big, in that case, that's a wastewater treatment plant. Very centralized, very separated. This only treats wastewater. This only generates electricity. And and those are massive. And I'm really want to try to think a bit more creatively and try to see what else we can do. First, we can go here where we start to become decentralized, but we're still separated. A great example are solar panels. You can have a solar panels on every roof. So now you're really much decentralized. You can generate electricity, again, in a very modular or decentralized way, but we're still very much separated. The other example is here is when we're still centralized, but now we start to be integrated. A great example for that is the smart tunnel in Kuala Lumpur. Kuala Lumpur, torrential rains. It's in a tropical, it's a tropical city. So they had a lot of congestion. So they built here an underground tunnel for cars. But whenever it rains, they close the tunnel and they flood it with stormwater. So a very cool example of, again, two problems. Instead of building that massive, remember in Chicago, we built that massive system, the TARP system, and all it's doing, it's really storing wastewater. And I think it's a waste of a big opportunity because building that costs billions and billions. There in Kuala Lumpur, they built the same infrastructure, but they were very smart. Instead of having one value, it has two values. So you start to integrate. Another example that I love, and for those of you who are in India right now, you're going to love it, and it's India, most populous country in the world. That means a lot of people need a lot of food. India is a country that's very, very hot. So you need to have an irrigation system, and there's an amazing irrigation system in India to bring water to fields to grow crops. India is very hot, so a lot of that water evaporates. How do you deal with that? How do you prevent water from evaporating? Well, the 20th century engineer is going to say, well, it's easy. The problem is the sun, right? So either we bury it or we cover it. That's the solution. And then problem solved. I'm an engineer. I'm happy. The 21st century engineer is like, no, we're going to think different. We're going to be smart. Let's do two things with one solution. Let's put solar panels on top of this canal. Sorry. So now we have the water that's there. We have the shade. So a lot less evaporation. So benefiting. And then the solar panels, because the air around the water is a bit cooler, the efficiency is increased. And we can use also the water here from the canals to clean the solar panels. This is a 21st century solution. And it's funny because when you realize it, when you hear it, you're like, of course, it's obvious. Why didn't I think about that before? And so that's why for me, it's really think different. Let's think more creatively. Doesn't mean more math, more modeling, more advancing science. It's really being more creative. And in that case is multifunctional, doing multiple things, really trying to leverage multiple things with one solution. Still localized because it's those canals and still integrated. And then we have integrated and decentralized, and might not come to a surprise that my favorite there is green infrastructure. Every single street in the entire world can be retrofitted with green infrastructure. So now that street is not only a transportation asset anymore, it's also a stormwater asset. So love that example. And I do with me really to a large extent if existing infrastructure systems practices lead to over-engineered systems. This is a great example. This is in Los Angeles. If you've ever seen Terminator 2, you have a big thing with that big truck and the motorcycle. It's in those open channels here. This is ugly. So yeah, sure, flooding problems, but don't do this. Do something different. Do something nicer. And there's really a way to think more creatively about that. There's one place in that my favorite in the whole world is in Korea, and there what they have is something like this, let's say, but also with trees and people can walk and it's a park and it's really, really nice. At some point in the past, I think 2 years ago now, I was on LinkedIn and there was a guy on LinkedIn I'm connected with who took this video of Dubai and who said, Dubai, city of the future. that person, very impressed. Dubai is the future. Look at that amazing infrastructure, amazing buildings. And I was like, no, this is not the city of the future. This is the city of the past. This here is Metropolis. This is a movie from 1927. Dubai is Metropolis. So this is not the city of the future. This is the city of the past. We've got to be more creative. We've got to think differently. One of my favorite example is this one here. So as many smalls are often better than one big. Paris has the Seine River comes here in Paris, and see, it's got a lot of the Seine River has a lot of affluence, and so with the specific rain patterns, all the water here can arrive in Paris at the same time. And in 1910, it was a massive flood; the entire city was flooded. And so to make sure that never happens again, what the city did was to build large reservoirs here, enormous reservoirs. And when it rains a lot, they fill those reservoirs to try to for the water here not to arrive at the same time in Paris. Again, 20th century solution, massive centralized systems. Right now, what they're trying to do is to be a lot smarter about that, because here you have those massive reservoirs that are not enough, by the way, but you also have a lot of small streams and affluents. And what they want to do is to flood those little affluents. And so they're going to work with farmers around, let me come back. They're going to work with farmers here, there, so that the farmers plant next to those streams crops that can actually withstand flooding for several weeks. So right now, if you put corn, for example, so there's a documentary, that one here that I highly recommend to everyone. It's on YouTube. You can watch it for free, and there's subtitles also. The subtitles are not perfect, but you can get them. And so there it was a farmer who's growing corn, and corn, if it's flooded, it's gone. But they were talking about mustard, and apparently mustard crops, even if they're flooded for several weeks, then you can still have those crops. You still, you can still harvest those crops. And so again, that's very, very smart for me, because the volume of the water they can store in all those streams is 6 times higher than whatever those great basins here can do. So think different, think more creatively, think multi-infrastructure. One last thing I want to talk about is infrastructure interrelationships, which is also that, see here, this is the demand for transportation. It's that one here. Demand for water is the blue one. Electricity here is the green one. And telecom here is the purple one. The one thing you'll notice here is that all those patterns are very, very similar. I've seen those a lot in electrical papers. I only see the electrical demand. In water papers, I see the water demand. In transport papers, I see transport demand. And then I have my transport people telling me, well, we want to beat congestion, so we'll have schemes and everything so people leave earlier home so that we don't have much congestion. And my answer to them is, sure, but if you do that, it's going to affect the electricity consumption. Have you talked to the people in electricity? And they don't. But really, we should, because those interrelationships are there. So interrelationship means that the way that you consume one really impacts the other. The reason why we have a peak here is because that's when people are home, they're preparing dinner, the sun starts to set, so you consume more electricity, you consume more water, people still are on the road. So those interrelationships are there. And so there's got to be ways to have policies that only focus on one infrastructure system, but on several. I always say that decisions that affect one infrastructure affect all infrastructure systems. So I'm not going to talk about that, but there's ways to capture those, and I've done a lot of work on that. One was to look at the consumption of electricity, gas, and water consumption in New York City. We got a lot of data with my students. We use machine learning. In that case, it's XGBoost, and we got some SHAP results. From the SHAP results, we saw that they were very much interrelated, but that those interrelationships were very complex. So we have to better understand them. With another student, what we did was to look at electricity transport. This one was in Chicago. We clustered places here, zip codes in Chicago, based on the electricity consumption. So purely using electricity data, we looked at whether there's electricity consumption profiles. And we found 6 profiles, and you see here the general curves, how it works. And what we found is that the one determining factor to predict which cluster you have has nothing to do with electricity, is in your transportation habits when you leave in the morning to go to work. And that really depends on where you live. So if you live downtown, you're gonna leave maybe a bit later. If you live here in the close, in the suburbs, you're gonna have to leave, much earlier to beat traffic. And then if you live further away, then you don't even go downtown Chicago, so you don't have to. So again, interrelationships are there. So even my electrical people here on the line, if you want to change the electricity consumption of people, you should talk to your transportation colleagues, because they're highly interrelated. So what's the future of infrastructure based on all we've talked about today now? Well, with water, of course, there's conservation. In a lot of places, it's really how do you consume less water, because We're consuming a lot of water. Places like Chicago, it's not as important. But really, I would like us to rethink distribution because those pipes always under pressure, for me, makes no sense whatsoever. It's a ticking time bomb. We've got to rethink it. With wastewater, well, it's really green infrastructure. We've got to make those surfaces more permeable so that whenever it rains, water can be stored locally. Plus, those green infrastructure, all the green here has tons of what's called ecosystem services, other benefits, lower ambient air temperature, increased biodiversity, usually increased air quality. And now even I'm trying to work with people to look at the health benefits of that green infrastructure. Transport, accessibility. So I didn't talk about that before, but when I say places are closer, so you don't have to go that far, that's accessibility. It's not physical accessibility. It's not for people with physical disabilities. It's accessibility is just how many places can you reach within 10 minutes, within 15 minutes, within 20 minutes. So by making destinations closer, you just generate a lot less congestion. With electricity, it's really renewable energy. And now we're getting much better at storing energy. So I'm not going to go there. But what we do is we generate a lot of electricity. When we have an excess, we can transform it to a different type of energy. So for example, in the battery, so that's chemical energy, and then we transfer it back to electricity. But we're going to consume a lot more electricity in the future. So we really need to think more creatively at how we can generate more electricity. Gas to me is gone. Everything we do with gas right now, we can substitute with electricity. So gas is gone, pretty much. Solid waste, it's really reduction, recycling, and that's also where we produce a little bit of gas, again, with that anaerobic digestion. Telecom, more or less, we're probably going to be having more telecom. It's really changing. If you want to know more about telecom and about satellites, low Earth orbit satellites and all that, really, again, read the infrastructure book. I have two big chapters on telecommunications. I explain how the phone works, and I explain how the internet works. Fascinating, absolutely fascinating. Again, get it for free. Okay, or give me 5 stars somewhere to make sure more people read it. And it's very, very easy to understand. And then the future for me, really, it's multifunctional. We've got to think multifunctional. We've got to think to be able to, whenever we build one infrastructure system, we build multiple things. Right now, for example, I'm working with the senior design team, and the senior design team, they're building a bridge, pedestrian bridge over a street. And I say, what else can you do? And what they can do is to have a stormwater infrastructure right there. And they can also put a telecom tower on top of that bridge. Multifunctional infrastructure. That's more sustainable. That's how we think different. But we also need to consider major trends. And very quickly, I want to talk about some of those major trends right now. Cities are shaped by the challenges that they face. What do we face right now? I was part of a UNEP report, United Nations Environmental Program. I worked on the GEO7 report. And there, the whole report is about addressing the 3+1 planetary crisis: climate change, air pollution, land degradation, biodiversity loss. How can we come up with infrastructure solutions that provide infrastructure services to people while addressing those crises? And the other big one that I'm really working on right now is depopulation. So I know we keep talking about cities getting bigger and more population. The reality is that right now we're arriving almost at a peak in the world population. We might be there, maybe we're there now. We're predicting 2050, 2060, but then we'll actually decline. And a lot of places are already depopulating. We always hear about Japan, we hear about Italy or places in Europe, but even the US, 40% of cities in the US are actually depopulating. So it's hard to see because it's a lot of those little red dots here, and they tend to be more in rural areas. But they're depopulating, which means that those places tend to have an excess of infrastructure. They have water pipes, they have roads with potholes, and all that infrastructure, maintaining it is becoming really a challenging. And so it's thinking about the future. How do we provide infrastructure systems, again, that don't become a burden? This is our projections for 2100 of cities that would be depopulating. So how do we do? We should know that right now, the amount of infrastructure that's in the world, what we've built as human beings, pretty much in the past 130 years, the mass of everything that we built, the mass, right, of all that exceeds all the biomass in the world. Take all the trees together, all the animals together, all of the natural environments, so not the rocks, right, the biomass, put all of it together, the weight of that is less than what we humans have built in the past 130 years. It's absolutely incredible. And this is a lot of infrastructure that's, aging, that's becoming a burden. So really rethinking, thinking creatively, being more multifunctional, being more sustainable. So just to finish, this is my last slide. Diminishing marginal returns, we must change. Design practices, let's be more creative. Let's think of interdependencies, interrelationships, and let's take into account those major trends when we think about the future of infrastructure. I'll finish with that one slide. that textbook if you want, with equations. If you don't want to go to the textbook, infrastructure book, very, very easy to read. I'm actually getting a lot of attention on it. It's done well. I'm super happy. And then what I'm doing now also is that Substack. So this is a newsletter that I have, and I send an email once a month. It's always the first Monday of the month about some infrastructure somewhere in the world. Always positive, always fun. That's where I published the one about poll reading. So how do you read your poll? So you can go and look at it, but I highly recommend that you just go there to that link. You just put your email. It's free for now. At some point, it might be paid, but for now, it's free. And then I'll never share your email with anyone, and then you're gonna get that email. So yeah, there's poll reading, there's infrastructure in Disney World, and I just had one now on Yam infrastructure, which is about the Mongol Empire. The Mongol Empire, largest empire in the history of the world. They all rely on one infrastructure. It's Yam infrastructure. What is it? How does it work? Sign up, go see my Substack. All right. Thank you very much. And I'll stop here. Whew.
Sounds good. Excellent.